Right. Good morning and welcome to yet another proposition. And it's my great pleasure to welcome Pritam Lenka, who is an architect by training. And he worked as an architect for several firms before going on to do his master's from Barcelona, master's in architecture. And he has been associated with academics since 2012, and he has also taught at various universities before he joined Sushant School of Design in 2020 as associate professor. So he's really straddling both worlds, and his research interests lie in exploring computational design technologies. Very contemporary field, and I think it's generated a lot of interest. I myself have received a lot of queries about from visiting faculty, etc., who've been very keen to join, and I hope they are going to do so from YouTube. So, with that, welcome everyone, and over to you, Pritam.
Yeah, thank you. Just give me a second so that I can present the screen. Yeah, is my screen visible?
Yes, it is.
Yeah, and I'm audible. Yep.
Yeah.
Thank you, Radha, and a very good morning to everyone present here. This is a quite, to be honest, a quite recent venture that I have done, particularly after the 2020 lockdown, which restricted a lot of things, but at the same time, it opened up a lot more avenues and forums, which I will talk later and will relate where did this thing come from. So I'll come to that later. But my proposition to teach, this is about teaching interior services, and I have been teaching interior services for quite like 3 or 4 years. But specifically, I was into the HVAC systems, the plumbing, and the electrical, and all that thing. Acoustics for me was a relatively is a relatively new topic. Why? Because it probably didn't find its place in the course curriculum in the earlier places where I was teaching, and it really struggled to cramp itself. But this time I tried to take it up as a research topic and just see that where I can get if I have this whole computational approach to it. So, running through the presentation, so a year ago, when we shifted from the physical classroom teaching to the online teaching and at the mercy of the Google Meet, there were certain things that was restricted and that they were important to design. They were important to architecture. One was site visits stopped. Second, the interaction with consultants and engineers and the other support people, it stopped. The face-to-face interaction, it stopped. And suddenly, I found myself, personally, I found it really, really difficult to deliver something where the mandatory requirement was to visit sites, to interact with consultants, to feel the physical world and the materials. And hence started my struggle with acoustics. Now, uh, when we stopped at this 2020 lockdown, then I started researching about online materials because the library was also closed. We could not issue books and refer to them. And I found out that there were a good amount of lectures by these two professors from IIT Kharagpur, who had around 40 lectures recorded spanning 8 weeks as a course for the NPTEL, which surprised me because generally we devoted around 5 lectures, one per week, so to cover up our syllabus of acoustics. So it was a tight schedule, and I thought, where do I start and how do I go about it? Just to begin with, I will just introduce everybody to everybody knows about the concepts of sound and acoustics, but really I just have to be on the common platform. So I just introduce certain terms and terminologies. One is called as the amplitude of the sound, which is in decibel. It measures the loudness of the sound. How loud somebody speaks is measured in decibel. The second most important thing is called as frequencies, and these are important terminologies. So it's called as frequency, which is the how many wavelengths per second. That's called as frequency. Nevertheless, the most important part in acoustics, and which is the most familiar part for designers, is that it follows a geometrical pattern. Though it's a wave in character, it's a wave motion in character. It follows a geometrical pattern and follows all those angles of incidence and the angles of reflection. So if it is a flat surface, then it reflects equally as per its angle of incidence. If it's a concave surface, then it concentrates at one point. If it's a convex surface where it hits, it dissipates or it gets diffused. And if it also behaves quite naturally with materials, when there is a softer material, then the things are getting absorbed, and when there is a reflective or a hard material, then the sound gets reflected quite quickly. So these are different terms and terminologies which are associated with acoustics, and they are a bit theoretical, which I agree. Um, Generally, when we talk about uh, giving or delivering a lecture in acoustics, we start from the historical references. We start from the Epidaurus, which is the Greek theater. We start appreciating the way it is oriented uh, to the wind, and the materials like the limestone that has been used there, which has the characteristic of high reflectivity to reflect the sound to the audiences, which probably has this theater has a radius of around 180 feet. And also the Roman theaters, and then we talk about a lot more Gothic cathedrals and everything. And then finally, we come to this hall, which is the Fogg Lecture Hall at the Harvard University, uh, which was at that time one of the most badly designed acoustic lecture hall, and for which Professor Clement Wallace Sabine was appointed to redesign the hall and treat it acoustically. He had a PhD in sound engineering, so he was appointed to uh, restructure the hall, and from where we get something which most of the architects and interior designers, they know, something which is called as the reverberation time. So the whole uh, course of acoustics is based on a mathematical platform, where we talk about something which is called as reverberation time. There is a certain formula to it. I'll just try to define it very simply. The reverberation time, it is the time that takes the sound to decay in 60 decibels. So the lower the reverberation time, the dead is the space. The higher the reverberation time, the live is the space. So particularly if we are looking for a recording room, then it has a very low reverberation time. But when we are looking into a church or a kind of an auditorium, it has a relatively high reverberation time. So once again, we have certain formulas, we have certain numbers. Also, it the RT also is related to something which is the volume of the whole space. It calculates the space in terms of numbers, and also certain things which is the surface area of materials that have been used in the space. So it also has a variable which is called as the coefficient of absorption. And this coefficient of absorption is what is given by these tables, which is different for different frequencies. And then after we give this kind of a broad background to the students, we that this whole thing leads to a solve a design problem. So that's the whole idea of how acoustics has been is being covered. Traditionally, we probably were taught in that manner. We are giving the lectures in that manner only, with some modifications and some new technologies and some introduction to new materials. So, this whole mathematics is something which was worrying me a lot, because that was something that the students were not able to grasp. But at the bottom line, the thing was, if it is all about building science, then it's all about maths, and if it is all about maths, then can it be put into a computer, and the computer could compute certain things and we design certain things. So that was where the thought um, arose, and I started researching more on this. So generally, the last semester was not up to the mark, because we were left at the mercy of Google Meet, and it was a one-way platform. So the first thing we changed this semester was, moved away from a one-way communication platform to a real-time interactive platform, where the Google Meet was a communication platform only to listen to the students. But we had something which is called as a concept board, where people could interact. Everybody could come together. They could draw. They could sketch. They could scribble, and we could all join together and scribble at the same time. So that saves a lot of time. That saves a lot of effort. And that was the main thing that happened, which resulted in making the drawings at least a little bit more perfect. The phase two of the services studio was not exactly a services studio. I had the privilege to take something which is called as CAD in semester 6. So I introduced the students to something which is Rhino as a platform. Why Rhino? We had other softwares. We have other parametric or generative software, if I can call them correctly. But why I introduced Rhino is because I have been practicing it since the last 6-7 years, so I could do a little bit of troubleshooting more quickly than other softwares. So I slowly introduced them to something from 3D modeling to something called as algorithmic design. So we did not draw a line, but we gave the parameters to draw a line. So that's very simply putting it. And we did not draw a circle. We gave a parameter, which is a radius, to draw a circle. So these are something we changed, and that helped me a lot, because services never gave that kind of a time or that kind of a belt to explore all those things digitally. Um, so this phase produced certain kind of drawings by the students, which were technically correct. They attempted some kind of line drawings. They attempted a lot of explored a lot of materials digitally, of course, and they were fundamentally clear about how the ray diagrams work, what is a source, and how reverberation time works, what is a reflection, what is a reflective surface, what is an absorptive surface, where to put and where not to put was based on their intuition. So this is, I was just comparing the results that we got in the first phase, where the recommended reverberation time for an auditorium lies somewhere between 1.5 to 1.8. And the results that these students were getting, we were making an Excel sheet, we are designing, and we were calculating all those areas for these things, adding it up, multiplying it with coefficients of absorptions of materials that have been used. And the students were getting somewhere around quite lower reverberation time, which was around 0.73 or 0.83, something like that. But they were not so supportive enough to once again change their design or review their design, because CAD gives you a very explicit way of working, that when you make a design, it becomes a little bit, they become a little bit hesitant to go and change that design and come once again with a new design and a new calculation. So we stopped at that stage only. Right now we have a next module after 1 week, where we have a 1.5 weeks of class, where we will explore these things digitally. So we laid certain outcomes for the acoustics. The first was understanding the key concepts governing acoustics, which I evaluated they have more or less learned about. The key concepts of acoustical treatment of a space and its validation through one Excel sheet and computing it tediously was also more or less achieved by a lot of people. And they could also explore certain custom and standard and custom made materials and details for acoustical design. The last outcome was still to be achieved, which is validation and simulation of digital prototypes. So we are supposed to, and this actually spreads into the CAD as a subject, not in services as a subject. So we will be taking these more drawings, we will be taking these technical drawings and making digital prototypes of it, and then validate and simulate it, which is a difficult task, not to make a 3D model, but how to validate it and how to simulate it. So this particular software, and there are many which also support the whole thing. So this particular software here, it translates all that thing which are given to the students in terms of a table, where from 65 hertz to 8000 hertz, that the frequency, the octave frequencies. We could find out that these things are all getting their inputs in this software only. So rather than looking into the tables, we could actually slide them according to our requirement, and we could actually control them parametrically. So that was one of the advantages that we got, that rather than doing a calculation, and the most common question that came to me during this period of a time, which column of frequencies should we take? But the obvious thing when we are talking about acoustics of a room is that there are certain higher frequencies, and there are certain lower frequencies. People speak in a higher frequency. There are some people speaking in a lower frequencies. Music in a higher frequency, bass in a lower frequency. So taking these things and once again computing the average of these things and making it into an Excel sheet always becomes tedious. So let the computer do the job. So we found out that the plugin and the platform had the same numbers. They had the same materials. We could have custom materials, and we could start just translating those tables into the software. So that was the first thing that we could do. Secondly, it might look a little bit alien, but we started looking into something called as the visual algorithms. So algorithms means they follow a certain process. So the way of calculating the reverberation time was translated into these kind of crazy wires, which the students did not make. I had to code them, and I had to struggle a lot to code them, because even I am not from the same background. But yes, taking some friends' help and taking some of the sessions, I could really do it. So, so these, if I just break this complex diagram, which makes no sense right now, into some kind of influencing parameters. So the audience, the source, and the space, they are more or less, and the space as in a digital prototype. So they are more or less concentrated here, and this is true for any kind of a space and any kind of an audience. So that's one. The reverberation time calculation across the 8 octaves from 65 hertz to 8000 hertz is contained in this tab only. So we could give the cutoff time, we could give the number of rays, as in the to increase the approximation thing and the accuracy. So we could do all that simulation. So these simulations are done by these tabs only. We need to only give the number of approximation and the number of accuracy rates based on the capacity of our computers, obviously. And all these things started calculating the reverberation time and giving us a range of frequencies. So where during the CAD exercises, people were designing and coming up with one numbers. Here we could actually get more than 7 frequencies along the range. We could take the average of these things and start calculating. The best part of using these algorithms is that it holds true for all the digital models that the students will prepare in the next week. And we will come up with around 15 to 16 different results, and we can then validate that whether this code holds true and what are the different reverberation time that we are coming across, and checking it once again with the CAD models and the CAD drawings they had made based on the theoretical knowledge. We could also simulate, because it's really hard when we talk about acoustics, and when we deliver those lectures, that this is how the sound will reflect. Nobody knows how the sound will reflect. So if the computer can do it for us, if the computer can at least simulate approximately the how the sound will move and how the sound will dissipate and where will it stop, then probably it will help us visually to understand certain spaces, certain bigger spaces, and certain ceilings, and certain sound traps, and certain resonance chambers. So, so we talked about this simulation code also. We gave it certain colors so that the intensity increases from red to blue. There's nothing related to the temperature. Then we talked about that the source, that means the sound source is all related to this tab only, and the geometry or the space that we are talking about is related to this tab only. So the algorithm remains the same. The spaces they change, and probably then we can test ourselves to different kind of spatial enclosures. This exercise is still pending. We are supposed to do it next week, and it's still pending. But we will have some good results. That's what I have in my, and that's what I aim. But it also left me with two questions. One, uh, what are the next steps that we could take from here so that it could validate our theoretical knowledge and make some study materials which will be easily accessible and understandable by the students. So the next thing, or the next step that I'm thinking of, is to actually simulate certain historical models. I came across this hypogeum in in a paper about this hypogeum in Malta, where they claimed that the chamber length, it's a three-story underground building. So they claim that the chamber length and the frequency of a particular sound wave, they are the same. And when there is a sound produced in this vault, it actually produces certain kind of interesting sound waves, which are all harmonic, and there's a feel about it. So I am putting this as my next phase of research, to start getting some drawings, some authentic drawings of it, and start modeling this and looking at the materials. Also, the baptistry of Pisa, so this has certain things which are called as the resonance chamber. So even if a person is singing along without any active systems, that means without any microphone and something, then there is a considerable amount of sound which becomes lively here, and it gets trapped in these chambers, and they really produce a beautiful sound and a beautiful acoustical environment. So can these things be computationally evaluated is something which I'm still thinking about. And the next thing is, if we are putting things into a parameter, whether we could find certain optimization, whether we could find 25 more models, digital models produced by the computer, and we can choose at least 5 or 6 out of it. So the whole approach goes from an explicit one to an evolutionary one. That means we are not actually going and we are not actually looking at going and changing the CAD drawings, but we are making the computer generate certain models for us from which we could choose some. So these are the two approaches which will be my way to look forward for. And regarding where this all started, it all started where this computational approach, where this algorithmic approach started. It all started, and sorry, before that, I also got a little bit of research. I did a little bit of research whether whatever we are doing in our academics and in terms of the studio projects, whether there is a practical or a approach to it. And I found out that by this thesis by Elena Badino in Sweden that there are a number of halls, there are a number of concert halls, there are a number of dance clubs and indoor installations which were all designed. And for acoustics, for their performance-based design, they could. I just highlighted the kind of software that I used and wherever they have been used to design the spaces acoustically. So it somewhere down the lines boosts my confidence and validates the point that yes, acoustics can be computationally approached. The shift, actually, I will be quick here. So the shift actually started last year when I attended this Digital Futures conference in which was never accessed before, and it happened in the it used to happen in Tongji University in China, and then due to lockdown they used to they opened it up for everybody. So this lecture influenced me a lot, and I started researching about computational design, the field of computational design, where do we lie, and what all we have actually explored. Probably we have I have personally explored something which is parametric and algorithm, where we are looking into the process driven through computers. What remains still unexplored is generative design, where there is optimization by the computational approach. Form finding, which never used to have a computational approach when Sir Fry Otto used to do it. But yes, today the form finding also is one of the major aspects of computational design. And I looked up at one thesis which talks about AI plus architecture, which is all about machine learning. But that's right now out of my scope. So that's the chronology where we lie. And I looked at certain practitioners. There are a lot whom I have missed in my presentation, but these are the people whom I follow. So that's the reason, and I know some of them personally. So that's the reason I put them. Samir Fedora working on the library, which has the thin shell structure. Urvi Seth doing a lot of work on INSEPT University on thin cell structures and computational design. Joy Mondal from the V Research Lab working on the Kalinga style of temples and their evolutions. And Monish working on interior thermal comfort through computational design, but looking at it in a vernacular way. There are other patrons from the from all across the world, Mark, and I have tried to put them very contextually, not looking at the formal approaches of other people also. So Jane and Mark Burry, who are appointed to design the for the construction of the Sagrada Familia, and they are approaching it computationally, looking at complex structures. Block Research Group, Philip Block and Akim Menges. So these are all pioneers on thin vault structures, and Samir Patora and their office used this Rhino vault and Hakim Menges work in order to build their design. And our own Sajay Bhusan from the ZHA or the Zahadid architects, looking at postmodern forms. I was also surprised that there are several organizations which are working on computational designs and which are giving a lot of material to us. Cadria, CAD Futures, and Digital Futures, and also certain journals and certain free open source papers and browsers. I was really surprised that CADRIA, which is the Association of CAD Aided Architectural Design Research in Asia, was hosted in 2005. By the TVB School of Architecture during that point of a time where Professor Anand Bhatt, A.G.K. Menon, and everybody, including Marx, were a part of it. And today I did got to know that Professor Urvi is now the secretary of this association of Career. So it's a whole a different group of people, but they are working it on an open source. So we can access that, and we can look into approaches where we can introduce these things into the academics. I'm a strong believer of that. Just as a conclusion, so I think when we start to use a skill-based subject such as CAD and improvise it into a knowledge-based subject such as services, I could get something which is a participatory design. That means the numbers and everything and the changes could happen, and the student and we could interact a lot. There was a collaborative approach. I could approach people who could do the whole thing. Uh, uh, it's all about performance driven design rather than a vendor approach and the material. Like people always say that acoustics, we have materials, we will install those materials, but it also validates certain performance to numbers. And but however, I have this apprehension that whether these numbers and results, how do we validate it in real life location and post occupancy? So these are certain conclusions, certain apprehensions that I would make after the study that I've been doing since the last 4 5 months. And last but not the least, I would like to thank these people. They had helped me a lot directly and indirectly. Rich, Subha Chaudhary, Jedi, who actually did the helped me a lot with coding. Shubha was my batchmate, and he recently completed his PhD in virtual co-design methodology in urban spatial design, where they were designing something where the public would participate in the urban design through certain apps and all, and obviously the IEA and the ID students. So thank you very much. I think I took a little bit of more time, but I could I don't have lots of rendering with me. I personally don't like renderings. So this is just a small simulation that we I tried to do with the auditorium that was designed by one of the students, and how sound was behaving when there is a source and when there is an audience, then how the sound is behaving, and how all those materials being put into their places with the coefficient of absorptions. So that's it from my side. I would really like suggestions, questions, and critiques on this approach of mine. Thank you.
Thank you, Pritam. And I have to apologize because I lost my internet connection in the middle, so didn't follow all the arguments. But I'd like to open it up for suggestions and feedback, questions. As far as I see, it was focusing on the education part, but I might be completely wrong. Yeah, about this. there's a comment in the chat from Sachin Dutt,
Yeah,
who's School of Design, who thanks you, Pritam, and says it's a very insightful. Simulations are extremely useful for forming hypotheses based on sound reasoning, which can be later tested in the real world. However, the output of a simulation is a number. If there was
yeah,
some way of connecting a number derived from simulation with actual sound experience, how a certain reverberation in a numerical form actually sounds like, then we can connect with the real aesthetic experience of a space. We can also look into aesthetics of sound. I think this is a comment as well as a question. I think good.
yeah.
Respond, yeah.
Yeah, so that was also where I was also concerned that every time we are getting certain numbers out of it, and if we had numbers, and probably it could lead to certain kind of geometry which has a special acoustical value. So that's what I was also thinking, if these frequencies could generate some kind of a geometry, and if there is a, psychological connect to it. So that's also I was thinking I could not research a lot of on it, but it was on my mind that can the reverse also happen? Can numbers produce certain valuable spaces and qualitative spaces?
Mhm. Yes.
Can I little bit come in?
Yes, please,
Yeah,
Professor
yes, sir.
Kusapa.
You see, this is in continuation of the question which came up. Because to me, this presentation is too dry. Because anything that you discuss about sound cannot be really understood unless there is a parallel.
Hmm.
And I think I have seen many such presentations on, sound and its sort of, uh, quality in a building, and its comparison with the computational processes that you were describing. But every time the presentation was accompanied by the resultant sound,
Hmm.
because because you see, ultimately it deals with a very sensitive aspect of our perception. And unless that is experienced, I think it only remains like numbers. And that's why I'm calling it very dry. So have you, the other thing, which I wanted to come at the end, but I'm sorry, I had to sort of jump in right now because some things cannot wait. You know, you mentioned about these 2, 3 examples that you were trying to now utilize, which are from West. Why don't you take something from our own context? Because I think sensitivity
Sir,
to sound, sensitivity to sound is in all cultures, and I think it is enormous. So I
Professor,
think,
I think there's some
see,
disturbance or from your end. Is everyone facing that? Uh,
yeah,
some,
no,
yeah.
but I'm in a soundproof room.
All right.
I think
Then we
if you
take it.
turn your mic off, Pritam and Radha, I think the network can probably support only one speaker at a time. That's it.
So I think I just wanted to mention these 2 things. I can take it up a little later on because this is an area, which is extremely close to, one's being, I would say.
yes, sir. I completely agree. Agree as in the sense that uh, I started it as a helping tool to the students, but then there were certain questions which at the moment came by when I was doing this research, that why couldn't these things happen? Why couldn't we deduce some kind of an experience in terms of this acoustics and everything, and why do we always end up with numbers? Because probably because computers do first generate, the easiest thing to do from a computer is to generate numbers. So I am really stuck at that point where I am struggling with the numbers. But maybe I could take it a bit forward. I could take a little bit of help from people who know how to move me forward with this line, and align myself to the sensory world. So
I can also mention why I'm so much, sort of interested in this. In late 60s, NID had a wonderful sound studio. And it was that time when they were actually trying to reduce sound into some kind of visual format, like barcodes and things like that, you see. And this is something, which in those days was also used in the monastery at Lature by Xenakis, because I think at that time these computational models were not available. So this barcode method of producing sound visually was something, which was really a kind of link between what you can do in the field of sound and what you can transfer in architecture. So this is something, which even at that time, I think Xenakis was a great musician. And since he was also an architect, I think he was trying to really, sort of deal with this idea as to in how many ways, you see, one can really orient, the perception of music in people. And I think Latour was one of the great examples of really combining this. And in NID, there were people, who were actually dealing with this, you see. I think NID in the beginning years, they did tremendous amount of work. And there were some people, who were extremely creative and bright, but unfortunately, in early 70s, everybody left, you see, because I think they really, felt somehow stifled in NID. And after leaving NID, they settled in West, and there they have done enormous amount of work, you see, in their fields. So our sort of orientation to somehow understanding music through different types of, fields was something, which actually started in those days, And, understanding music by listening, by experiencing, by somehow, working on design where sound was considered the primary focus, and developing a design, which really later on requires least amount of intervention was the goal of an architect, you see, in those days. And that's why when Kant designed an auditorium for I Am Here, he used to call it a violin, because I mean that was the kind of preparedness, you see, one had to really, do in order to translate, the ideas into a built form, which will also become like a musical instrument. And, this was the trend in those days. You see, for example, if you went and saw Berlin Philharmonic, I think that had the least later corrections in terms of sound. So architects were tuned, to train like this, you see. And if you see our own traditional examples, I think you will really discover something which is magnificent, and which also really tells us how sensitive our people were, to sound, because for example, every temple was an instrument, which was a kind of performance place, and music played a tremendous role there. So like a Gothic church, you see, I mean, Gothic church cannot be understood unless you really understand the importance of music in it with the organ. So this is something, which I think has to be somehow married when you talk about, algorithms and things like that, you see, because I think unless you marry these two, the subject might become a little bit dry, you see. I mean, this is my belief. Thank you.
Yes, sir. Completely agree, sir. I'll pick up.
Thank you, Professor Karma.
Can I be bold
Yes.
enough to jump in as well? Sorry, just taking. I think your methodology raises larger questions of your concern about validation. I think you need to kind of, I feel, assess what your systems of validation are and for whom. Because very often we are drawn towards a scientific validation and layer the original intention with another theoretical method that then eventually takes us twice away from the object of study. For example, the magnificent building sections you showed, and what Professor Savas also talked about, the temples, and you simulating it with computational tools, and therefore arriving at a formula that works in that does not necessarily mean it. Obviously, it means they did not use the computer to design those buildings. So, for example, the vitamin list sticker on a banana is not going to produce the banana. What are you going to do with that ingredient, vitamin sticker that is put on the fruit saying it has so much energy, so much calories, so much vitamin A, so much potassium, and the rest of it? If you arrange those ingredients in a lab, it's not going to come up with the apple or a banana. What I'm suggesting is that numbers per se, to my mind, are not the problem. We've always worked with numbers since our ancient civilization. We have generated new numbers like 0. Don't need to remind everybody that. Numbers is not a new idea. The problem is whether the numbers are helping you to homogenize, standardize, or individualize. That is the trick. How do you play with numbers in order to enter into the psychology of a person where the hearing of the sound plays on your mind, and therefore, as you mentioned, psychology, memory, experience, upbringing, nurture, nature, all those things will play on how you perceive that sound. And indeed, it would be interesting, just aside, to study why one hears sounds in our heads when there is no sound. So even a situation, I was watching the film, Bengali film recently, and this character said that, certain situations demand an orchestra, and he's sitting in a restaurant and he's seeing two people argue or quarreling, and then he's playing that orchestra in his head without even hearing what they're saying. So I think it's a wonderful topic, Pritam, and I congratulate you for choosing this very interesting layered topic, and I hope you will keep the complexity and the layering of it to see where you go, and also kind of engage with the subjective, the non-quantifiable elements as well of sound, and to my mind, subjective experience is more reliable than objective experience because it's closer to one's experience, closer to the truth, whatever that may be. So these were the some of the comments that validation, what yardstick you're choosing for what, who is the audience for this validation, you, or are you trying to enter into how exactly, what were the testing instruments of the time? Surely they must have had some testing instruments to arrive at the solutions they did, and why do you need to standardize? What does standardizing achieve, and is there a cultural specificity of this audio experience? So these were some of the connected thoughts from the previous two conversations.
Can I also add a little bit in terms of suggestion to you,
Yes, sir.
Professor? Uh, you showed a wonderful, group of people who are sort of helping you or who are sort of associated with the kind of work that you're doing. I think you should also put some musicians who can talk about sound. There are some of them who are excellent. You see, because like what Professor Sasdev was talking about, sound in your mind, and that's where you begin. It's exactly similar. You see, for visual things. You see, for example, you must have an eye, to sort of perceive things, that you see, and the cone of the eye is so important. Likewise, I think your ears. I mean, look at the shape of your ears. You showed in your first figure. I mean, that is a fantastic acoustic with which you are born with. So I think you should also have a kind of sort of people whom you can talk to who are experts in producing sound. And I think ultimately each musician is, I mean, his struggle in life is to understand the phenomena of sound. That's why they talk about sound coming from throat or sound coming from mouth or sound coming from your solar plexus. So I think it would be a great idea to combine these two and develop something, for teaching. And that would give a fantastic understanding to students, you see.
Yes. Yes, sir. Maybe on the way to quantifying things, somewhere down the line, I overlooked the qualitative aspects, and I will look into these things and I'll put them together so that they both can marry, and I can have certain more interesting questions to this thing.
Thank you.
The other thing is, I would suggest, I mean, pardon me for suggesting, but I think in terms of listening, I think you should listen to a lady, musician called, you know, uh, 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 Kishori Amonkar talking about sound. And on the other, Leonid Bernstein's lecture to the students on music. And they only talk of sound. I mean, this could really open up, you see, the entire topic for your students, you see. And then you get into the nitty-gritties in terms of computational, methods.
Yes, sir.
Thank you. I remember, seeing your image of Sagrada Familia when I was a student of architecture. I remember one of our professors telling us that there was I think a rock band. I'm not sure if it was Pink Floyd, who's actually got a whole album or definitely a song as an ode to Sagrada Familia. And I don't know if that's going to help you or not, but just something that came up with all this talk of musicians as well, because they have some other understanding of space. And so Marina has a question. She says it was an interesting presentation, and out of curiosity, how is computational design different from parametric design? And do you think algorithmic thinking is the way forward? And just very quickly, I'm just going to also read out Sachin's comment. It's, I think, a follow-up. And he said the last video simulation showed a promise where we could see sound waves reflecting from the walls that could give some idea of how the sound will work. So that was just. But yeah, Marina's question about computational design and its difference from parametric design.
Yeah. Okay. This is a quite a debatable topic on different people perceiving it in different way. But as far as my research and reading goes for this thing, so computational design, people theoretically term it as the whole. It's the bigger umbrella of things. And when we approach parametric design, then we end up in only having certain formal or form based results. So that's where people like Patrick Schumacher and his whole idea of parametricism comes in. But then the way forward is to look at algorithms where they do drive a process of design. Particularly in taking a small example where if an algorithm of acoustical treatment could result in a better theater. So that is where the process is driven, and that is where algorithms come into place. Parameters and parametric design generally are associated with all those crazy and Zahari forms, so to say. So that's an area which is very easy to fall into trap with. I have been to where you are really amazed what kind of forms the computer do generate, but it's also really needed to get out of it and think ahead, where you don't produce fancy forms. I hope that answers the question.
I don't know if Marina is, yeah, Marina is here. I hope it did answer her question. Aruna, did you have a,
Yeah, I just want to say, I think fabulous area of research, and I think you made anyhow this whole area of parametrics and is something that has been intriguing. And why don't we have a faculty workshop, for the faculty, and we can kind of see you can do something. So this is I'm just saying it out there. So if we can work it out in June or something, I think, because
Yes, that's on our to-do list, Aruna, as one of the FTPs. I know
yes, yes.
we need it, and as soon as we settle with this, with all that's going on, hopefully as soon as possible we'll do that. That's on the anvil.
So Pritam has made this possible. It seems reachable. So thank you.
My privilege, man.
right? Are there any other questions or comments? Or suggestion? I mean, we have had a lot of suggestions for.
Just a general comment on this. I mean, it is a new trend in a way, and not so new trend everywhere, to kind of make the invisible visible, and then study the visible in order to track the invisible. It's happened with Corona. It's happened with, and your simulation model also, reminds me of, not in terms of the devastation, but reminds me of the virus, which is kind of has its own and trajectory, and probably it's because the what we know about the virus is the physics of the particle, it's not even an organism. I don't know what you would call it, but it's largely to do with how much it floats, how much it sinks, and how making the invisible visible through computational design therefore will alter our perception of the invisible, and we need to kind of just be careful about whether we are limiting our realms of perception because of that. Just to
Thank you. I think we can end on that, the visible and the invisible. If there are no other uh, uh, comments or questions. All right. Thank you very much, Pritam. And yeah, it was, I'm sorry that I had to miss some of it. And in fact, some of us maybe more, but we're going to catch the recording, definitely. And yeah, I've just received a message from Professor Menon that he also was unable to join because of poor connectivity. So anyway, we'll make the recording available, of course, to everyone. All right.
Yeah.
Well, thank you, Pritam, and look forward to follow up propositions also. That will be great. And
Yeah.
thank you everyone for joining in. And once again, thanks to Srijani, Sobhya, and Sachin, also Tayali, for all the support. And we'll see you in 2 weeks. And we have Tayali who's going to be presenting in 2 weeks from now. All right. Thanks everyone. Have a good day. Bye.
Thank you. Thank you so much.
Thank you, sir.
Thank you, sir.
Thank you.